We are going to cover a few examples of the concepts that we have discussed so far under steady-state seepage and also under pressure diffusion consolidation. Let's consider the first example with very easy boundary conditions. So we do this exercise for the sake of clarity, not to bring extreme cases to the discussion. So this is a large, let's say, concrete block that is stopping water on the left, and only a film of water comes out on the right. All the seepage takes place beneath the concrete block in this porous medium, which rests on a very low permeability sediment. For the sake of discussion, we are going to assume zero permeability. It doesn't have to be, but that's the condition we will assume. The first observation that we need to do, because our goal is to solve Laplace's equation, and as well as Darcy conditions to understand how much seepage is going to go under the concrete block, the first step, regardless of how we're going to solve it, is to identify the boundary conditions. In this simple case, we can think of being a water droplet at the inlet on the left-hand side, and if you were a drop of ink and you place yourself somewhere in the reservoir on the left, how would you migrate from left to right? That would be a flow line. And that flow line would come back and exit on the right-hand side. What would be the shortest path? Well, the shortest path is if you place a drop of ink right here on the edge, and that will follow this inner side of the concrete block until it comes to the left. So this is probably what we are going to call the shortest flow line. On the other hand, if I place a drop of ink all the way upstream, that one will sink in and will come along this lowest boundary all the way until it exits all the way in the far right. Therefore, this lower line has to be the longest flow line. And so this is also a flow line, and this is the longest one. And all the flow from left to right will be constrained between these two flow lines, which actually define a big channel. The next two boundary conditions that we have to identify is where does all flow start within the porous medium and where does it end? It starts on the first equipotential and it will end on the last equipotential. So clearly our first equipotential has to be here, the level where the sediment is at the interface with the reservoir, and we're going to check on that, but for lack of colors, let me dash this one. This will be the first equipotential, and where all the flow ends has to be the last equipotential, which I'm also dashing here to visualize it clearly on the projection. So this is the last equipotential. To summarize, all the water will come in between the first and the last flow line, starting at the first equipotential and ending at the last equipotential. And now the only thing that we need to do is to be able to solve Laplace's equation to get the total head everywhere else. Because, as you may remember, if you know the total head at any location, this is equal to h elevation plus h pressure, and if the medium has an isotropic permeability, then the Laplace equation tells us that the second of h total with respect to x twice plus the second of h total with respect to z twice is equal to 0. Once again, as you may have heard me already in previous videos, it is so surprising and important to realize that permeability is not part of Laplace's equation. What I'm saying is that the distribution of the total head how this mountain of total energy decreases from the first equipotential to the last equipotential is not a function of permeability. And you may say, well, but if it is anisotropic permeability, Kx and Kz remain. Well, you can multiply both sides or divide both sides by 1 over Kz, and what remains is Kx over Kz, or Kz over Kx. The anisotropy remains and has some effect. Actually, what it does is stretches the geometry, deforms the geometry, but the actual value of permeability vanishes. On the other hand, when we want to compute the flow underneath the dam, this will be KIA. Therefore, permeability or hydraulic conductivity in this case will play a direct linear effect, huge effect. So now that we have solved the first part, which is to identify the boundary conditions, the only thing that we have to do next is to solve Laplace's equation, because once we know the total head everywhere, we will be able to measure the elevation from a datum, and we're going to place the datum at the bottom of all our measurements. Let's put the datum for elevations here. And if we measure elevation from the datum and we know the total head, we will know the pressure head. And of course, remember that once you know the pressure head, or it will be the same as placing a piezometer, piezometric head or pressure head, you can compute the pore pressure, which is H pressure times gamma water. And if you know the pore pressure, you will be able to infer the effective stress and strength, the resistance of the system. The problem is solved. Let's just finalize this by setting up what are the values of the total head. At the first equipotential is elevation to the first equipotential is 7, and if we place a piezometer here, the water will rise to the reservoir level, so 6 meters plus 7 meters. This H total is equal to 13 meters. And at the exit, we'll do the same. It's elevation 7 meters plus, if we place a piezometer, the water will rise to the free water table, to the free level of the water, which is 1 meter. So this last equipotential has 8 meters of total energy. The conditions are set for us to solve our problem. The homework or the exercise requires that you do it first graphically. And so graphically, what we are going to do is to draw flow lines and intermediate equipotential lines so that we satisfy Laplace's equation, and that requires pretty much that flow lines and equipotential lines intersect physics, but because of physics, at normal conditions, normality. And in order to simplify the sketching and the analysis, we want to form between consecutive flow lines and parallel equipotentials, we want to create squares, or geometry such as a circle would touch all the boundaries. Please recognize that the problem is symmetric from left to right, and so the easiest way to start is to draw the line of symmetry, and the line of symmetry will be here, and that is one equipotential. The energy started at 13, we are going to end at 8, we lose 5 meters of energy. That means that up to the middle point we have lost 2.5. That means that the equipotential energy or the total head at this first equipotential is going to be 10.5 meters. We have 2.5 more meters to lose to reach the last equipotential, and we have already lost 2.5 meters from the first one. Now, we are going to choose for simplicity, we are going to choose the fact that we are going to have only 2 channels to make it simplest, and given the problem, then and the fact that we want to satisfy the formation of a square, the next equipotential has to be here and here and here before we reach the edge, where things are going to change, and then you can correct me there. This one is probably further to the right. And we are quite okay until we begin to reach the edge, because at that point it will have to begin opening up. because this is going to tilt. The idea is to migrate in that direction, but who knows exactly how we're going to get there. So if we go like that, this will have to go deeper. And let me not iterate anymore. This is not a pretty flow net, but it serves the purpose for this exercise. Please do a nicer version of that as you have time for another iteration. This has to be symmetric, so you only need to solve 1/2, but here I am trying to sketch this. Please, even though this is documented in this video, let me insist this is not a final flow net. This would be a first iteration, and you can identify lots of failures to satisfy this concept of a squarosity or normality in this case. So please correct in successive iterations. But it is good to get started. And the rest, please follow the guidelines in the previous video, how to solve a flow net. But the most important step, regardless of the solution, was to get the boundary conditions. We are done. And I also wanted to highlight that the intermediate one is clearly, because of symmetry, an equipotential, and we know from the beginning what is the total energy, the total head at that equipotential. Now we can say, and I'm going to solve it only for this case, if the point was at a certain elevation, in the problem is at the point is 2 meters high out of 4 meters, so a point B rests here. So this point B is 2 meters high. So that is the elevation. And what is the total head is 10.5. So the total head is 10.5, the elevation is 2, so the pressure head is 8.5. So if I would place a piezometer at this point, how high will the water go up? It will go up in the piezometer 8.5 meters to a total head of 10.5. So this is 7, 10.5. It would come somewhere here. And this is HP equals 8.5, given that the height is 2 meters. Now, if we know the pressure head, or the height in the piezometer, we know the pore pressure. And now the total stress, for this case, given the geometry and the symmetry, the total stress will be the weight of everything above, which is the weight of the concrete times the height of the concrete plus the weight of the saturated sediment, this 2 meters, times this elevation, which is 2 meters, H soil. The pore pressure is equal to H pressure times gamma water, and the effective stress will be E sigma minus U. And we do that for point B. If there is a point A far on the left, away from the influence of the concrete, you can do the same. Otherwise, your stress field is more complex. And the same you can do with point C. The second part of the problem requires that the solution of the Laplace's equation is obtained by finite differences. So let's rewrite once again Laplace's equation, the second of H total with respect to x twice, which by the time we discretize and we get the second derivatives in x and y, as you may remember, we ended up with a kernel where the total value of the head at the center point is equal to the average of the total head of the neighboring points. So H total above plus H total below plus H total to the left and H total to the right. That becomes the kernel. So if we have a grid and we place the kernel at this centered location, we take the value of the node above, left, below, right. We get the average and we replace it at the center, and we keep moving the kernel until the values don't change anymore. A few points to remember is that For this node, for example, there are no problems because you place the kernel here. If this was the discretization, imagine that this was a square grid and above, left, and right. But if you were on a discretized system where the point is here, now the kernel is here, and then you wonder what is the total head that you consider at this point that doesn't exist. And because there is no fluid flow across this aquitard, what we are going to do is to say that this is a fictitious point where the total head is the same as the total head of the point above. So the kernel becomes the value to the left, the value to the right, twice the value above divided by 4. And you can use similar concepts for the point here beneath the concrete block and from points far away. When you do the numerical solution, as well as the graphical solution, it is critical to put the boundaries far away so they don't disturb the problem. So if I sketch this block once again, what you would like to do is not to put the boundaries nearby, but actually extend them. Only the computer is going to do a little bit more work. And you extend them and you put them 2-3 times away from where some characteristic length scale that is important here. So I would take the height of the sediment, multiply it by 3, and put the boundaries somewhere here. Height of the sediment, 1, 2, 3, somewhere here. And now what values will you adopt in the far field? Well, in the far field, you can assume that the system is hydrostatic. So you put the same total head. So if all these values were 13 here, all the nodes started with 13, then here at the column you can also, on the vertical, you can also put 13. In other words, the system is quasi-hydrostatic in the far field, like a swimming pool. And now everything else is well defined, and you can solve it numerically. The second problem was a problem designed for us to help us understand what is permeability, or in the special case of water flowing through, the hydraulic conductivity in a soil. And remember, we started with Leonardo's parachute. It was all about the balance between the drag force, which is resisting, and the driving force, in this case, given by the pressure difference at the entrance and the outlet. And if the tube is inclined, also the gravimetric effect, which we're going to come back and bring it in the context of the total head at the entry and the outlet. And we concluded the size of the tube has a huge effect. It scales with r radius to the 4th. Now all these are constants, pi, 8, gamma water, the unit weight of water, and the viscosity are constant for a given tube with no R4. And if the tubes have a certain length L, the gradient is the head at the inlet minus the total head at the outlet divided by the length, which is the gradient. And please recognize that all this is known a priori before we solve the problem for a given tube. Now let's explore a porous network. And these are, I'm going to draw single lines, but these are all tubes. We're going to replace the tube, not by infinitely long parallel tubes like Coseni-Karman did. We're going to replace it by a porous network of tubes which not necessarily have the same diameter or the same radius. And we're going to create this for simplicity, otherwise L is not a constant. For simplicity here, we're going to assume that L is the same in both x and y directions. So this is L and this is L. Now, once again, for each tube, you know the radius, you know the length, all these are constants. So for each tube, you have alpha, if we call that quantity alpha. And so, you know, converging to a node, you know the alpha values for all the tubes that converge to this node. And now that means something very valuable, because all the fluid that converges to that tube must come out of that tube. And so we can add all the Q ins and the Q outs. And the only thing that we need to do is to solve for the total head at the center. And so we are going to, once again, call this to the left, this one to the right, this below, and that one above. And as you may remember, go back to the previous video, the H total at the center is going to be, these are tubes, this is no finite difference of Laplace. This is mass conservation at the node where 4 tubes converge in this case. It's going to be alpha H total to the left, H total to the left, alpha to the left, plus alpha. So the total head at the center node becomes this weighted average of the total heads at the neighboring nodes, weighted by the alpha values, which is this whole factor for each tube. Each tube may have a different radius, and so you will have to compute alpha value for each tube. And this is the way we proceed. So now we know the total head. We assign the total heads at the entry point, so those values are known. And in this case, I'm simplifying it. I think that in the homework is 10 by 10. We know the total heads at the exit points, so there is nothing to compute. And we can place that kernel at any point, like we did here, this point. And you can compute the new updated value for the value at the center. And you keep moving the kernel around until the values don't change anymore, and that means that the system has reached equilibrium or the asymptotic condition. The only trick that remains is to say what is the value at this node. This is a flow channel, as you can see, multiple segments, and so there is no connector at the bottom, but as you can see, we go back to the fundamental mass conservation equation. All the fluid that comes in and goes out of this node has to be such that the sum of the flow from the left, from the top, and from the right add up to 0. And therefore, instead of having all these 4 terms, in this case, you're only going to have 3 terms. To the left, to the right, above, divided by the alpha values left, right, and above, and there is no below component. The opposite happens to the top. Now you can create a pore size distribution, because we know that in logarithmic scale, in logarithms of the radius, making it dimensionless for the logarithm, the pore size distribution tends to follow a log normal distribution. That means normal in logarithmic scale. And by the way, this the point to the inflection point divided the mean tends to give you sigma over the mean, which is the coefficient of variation, tends to be in the order of 0.4 for most soils. So now you can play with that. You can create a log normal distribution, replace the tubes randomly oriented with log normal distribution, and recompute the flows. You can do something else. You can create layer systems, or you can create a correlation length, and you gradually begin to see how flow channeling will emerge, which has a huge effect on the hydraulic conductivity of soils. The next problem that we are going to solve is the case in which we squeeze sponge, in this case the saturated soil, and we are going to feel how the water squeezes out in time and to gradually reach a new state of equilibrium. Therefore, this is a transient condition, and we have already shown, starting from mass conservation, that this is the type of equation that we got. Now, please recognize that the change in void ratio with respect to 1 plus the void ratio is the volumetric strain. This is a 1D problem under 1D conditions, constrained. You cannot have lateral strain. The volumetric strain becomes the vertical strain. And the ratio between the stress increment that caused the vertical strain to the value of the strain is the constraint modulus. The reason why there is a negative sign here and allows me to flip this parenthesis is because the void ratio decreases as the effective stress increases. So this is what we call the constraint modulus, the inverse of the constraint modulus. This is the permeability. And if we assume that these parameters are constant, permeability and constraint modulus as the soil squeezes, and if the change in stress that call all this transient remains constant, in other words, we put the load and we let it evolve, then this term disappears. All this becomes equal to gamma water over K constraint modulus times du dt. Now, the second change of the pressure in depth related to the rate of pressure dissipation in time is a diffusion equation. So this is actually the inverse of the diffusion equation, and in fact we put it on the other side and we say that CV is equal to the second of U with respect to Z twice, and that is equal to the rate of change of the pore pressure. Indeed, this is a classical diffusion problem like thermal diffusion and chemical diffusion, in this case for the time rate of the water escape as the soil squeezes. When we place this in finite difference form, then this relates to the pore pressure above, to the center, and below. And this one tells us that the pore pressure now are going to determine the pore pressure at the next stage. So we rewrote that in finite difference form, and we said that the pore pressure next at the central point is going to be equal to the pore pressure at the center point plus beta, the pore pressure above minus 2, the pore pressure at the center plus the pore pressure below. Let me explain what that is. And if we have a grid, and we are solving this in a grid with the delta Z spacing and in time with the delta T spacing, so the pore pressure at the next instant at a given point will be related to the pore pressure in the neighboring points and the point itself in the previous time. So this is at time t, and this is at time t plus delta t, according to this equation where beta comes from, here is the ratio of CV over delta Z squared times delta T. So CV times delta T, or divided delta Z squared. And for convergence, we want this to remain greater than 0.5. In other words, when we begin moving the kernel about our time and space, this is space and this is time. When we begin moving the kernel in time and space, and we solve for the pore pressure at every point, what we have actually done is solve the diffusion equation, or the one-dimensional consolidation equation. Please, I insist that to get to this point, we have made a large number of assumptions. In this case alone, that K is constant, that the constraint modulus is constant, and that the applied stress remains constant. This may not be the case in your problem, so you have to go up in the stack of the derivation and remove some of those assumptions to be able to capture the problem that you have at hand. In particular, you may remember that the permeability is changing with the void ratio. So if we plot permeability in logarithmic scale and void ratio in logarithmic scale, these are straight lines. And that means that as the void ratio decreases during compaction, the permeability will decrease. And furthermore, if we plot void ratios versus effective stress, and this is also in logarithmic scale, and this is void ratio, you remember that these tend to be asymptotic trends. Typically, we tend to plot them in, this was in linear scale. And if we plot them in logarithmic scale, we stretch the axis at the small values, and this is going to look like that. Now, the slope at any point The secant at any point is that constraint modulus that we are talking about. And as you can see, the constraint modulus is indeed changing as the void ratio decreases or the effective stress increases. Now, in order to get to this equation, we assume that these values were constant. But if this is a bad approximation for your problem, please go higher up in the stack of the derivations and use the right form of the equation. With this in mind, let's come back and solve a problem which is quite relevant for all laboratory testing and is the basis for the interpretation of field data as well. So let's solve an example. We are going to do the case of a consolidation test. So we have a rigid wall oedometer. We have the specimen, and we are going to assume that the specimen has a double drainage. So there is a porous tone at the bottom and at the top. It has an initial stress applied. And now we are going to apply the change in stress. That is the one that is going to cause the step load that we're going to analyze. And we can have values. For example, this delta sigma, we can say that is a value of 100 kPa, a significant stress change. And the specimen height at this point, we can say that it was height A. So the first column in our calculation, whether it is in an Excel or in any algorithm, would be to place a height of the specimen, so the coordinate z. So at the top is 0. At the bottom, we are going to have a value of a. This is the last element that we're going to have. And we can decide how many elements we want, but the next increment is such that we can say that between any two successive elements, there is a delta z increment until we get to A. Now, for this situation, and this is the simplest of all cases, let's say that at the beginning the pore pressure was very small because the specimen is only 1 centimeter, it was drained, so let's forget about all elevation pressures, etc. Let's just consider the excess pore pressure that we are going to trigger by applying the load delta sigma. So the initial pore pressure is equal to the delta sigma that was applied. So now every point will have a value of 100. And this is our initial boundary condition. The next series of columns are going to see the evolution of pore pressure in time. So the next series, once again, is going to be dedicated for the evolution of the excess pore pressure as time passes by. So this will be for the time equal to the first time increment, and then we can have for the second time increment, etc., until we drain all the excess pore pressure. So this series of columns is going to be for excess pore pressure. Now, at time where time is increasing in this direction, at time delta t, immediately after the load application, within that delta t, the pore pressure on the two drainage boundaries will drop to 0. So we know that condition as well. Before I go any further, I notice that we have an increment in time of delta t, an increment in depth delta z, and the criterion that we had before was that beta equals CV times delta t over delta z squared has to be less than 0.5 for this type of finite difference approximation that we have done. Other finite difference approximations may have a different convergence criterion or a stability criterion. But in any case, we can place the kernel in the next point to compute the value at this position. And you realize that this is also going to be 100 because nothing has dissipated. And so the above, the below, minus twice the center is going to be 0, plus the center, this is still going to be 100, and the same will happen with this value here. So in other words, there has been only dissipation on the boundaries that we have drained right away. But as time passes by, the kernel is going to begin propagating the diffusion front further and further in until all the excess pore pressure has dissipated. The next set of columns is going to address what happens to the effective stress. And so, once again, we're going to evolve in time, but now I'm going to look at the change in effective stress. This is in the z direction. And what happens when pore pressure dissipates is at the beginning, the water took all the load. But as the water can escape, the skeleton must take the load by equilibrium. So the applied load minus the remaining excess load is going to give us, so this is the delta sigma applied minus U excess, is going to tell us the change in effective stress that the element has experienced. This is the applied load. This is the remaining excess pore pressure. If the pore pressure is not taking the load, the skeleton must be taking the load. And that is for the next sequence of columns until all the pore pressure dissipates. In other words, until the soil skeleton has increased its effective stress by 100. Now we can go to the next series of rows, and you can think of this as having different tags in the spreadsheet, or a very simple algorithmic solution. Once again, we're going to evolve in time, but what we would like to compute is the vertical strain. And the vertical strain is equal to the change in effective stress divided the constraint modulus. This is linear theory. We are assuming that the constraint modulus remains constant. So every value here will be related to the corresponding column at the corresponding time in effective stress, as epsilon z is equal to delta sigma effective over the constraint modulus. But we don't know the constraint modulus. So there are two possibilities here. This is one of the parameters that we can resolve, or you will see what is the trick that the geotechnical community uses. In any case, let's assume for a second that you know it. If I add up all the strains in all the elements and I multiply times delta z, I'm going to get, for each element here, I'm going to get the settlement. And the settlement at each time t is going to be equal to the delta z times epsilon z, the one we just computed, and the summation of all these values. The final column here will give me the settlement at times t equal infinite. Now, if I divide the settlement at times t divided the settlement at times infinite, now look what happens. The constraint modulus cancels out, and this is not a function of the constraint modulus in linear theory. And so this is what we actually do in the typical interpretation, the old methods of interpretation. We divide the settlement that we measure, the contraction of the specimen, by the ultimate contraction of the specimen at the end of consolidation, and we call that the degree of consolidation. And then it's not affected by the constraint modulus. And this is the end of the story, because now that you have plotted the deformation normalized by the ultimate deformation, and you plot your experimental data in the same way, the only thing that you have to do is plot this measure deformation normalized by the measured deformation at times infinite. And you can also superimpose on the same plot the settlement that you have computed at time t over the settlement that you have computed at times infinite. And these curves are going to look like that. And you have to go back. And somewhere here, you had a value of the diffusion coefficient, or which is equal to C sub v. You had this value, and this becomes your variable. Delta z and delta t are the same, and you just begin shifting the C sub v until you're measured and you're predicted. So these are the deltas, these are the settlements in the terminology that we have just used, until these two curves superimpose, and that is your C sub v coefficient. But this can get much more interesting, because if you have all the time steps, all the loads, let's say that you did a stage loading, you increase the load in steps, and you waited for the end of consolidation. Now what you can do is not only fit the diffusion coefficient for each step, and the diffusion coefficient is changing, but because you know the settlement at the end of it, you know the evolution of void ratio with effective stress. So you know this curve. You know void ratio versus effective stress in logarithmic scale. This is like that. And in linear scale, it would have been the exponential decay. And then you know the compressibility. Now you have another parameter to resolve, which is the permeability. And the permeability is evolving with void ratio. And for a given soil, it's evolving with void ratio. This is for multiple soils. And now you can infer both your permeability curve, your compressibility curve from a single test. You can do other things. We got into this diffusion equation by assuming that the total stress was constant during that step. But you could have constant rate of loading. And if you have constant rate of loading, now you have to go back one level up in the diffusion equation. And what you had was as follows. The second of u with respect to z twice is equal to gamma water over km, but this is the rate of u with respect to t minus the rate of loading with respect to t. And so now I can put into this, as time passes by, I can also put the change in load. Please go back to the previous video on the numerical solution of the diffusion equation. And now you can run tests with constant rate of loading or with any rate of loading. And you can go to the field and do exactly the same to analyze settlement data from preload tests. This is so simple and it's so powerful. Go ahead, give it a try.